Section 5.5 is going to sort of introduce our last new rule that we're going to be working with as far as gateways are concerned. And it's not a terribly difficult one. It mimics a lot of what you know about the function e to the x, but this is a base other than e. So it's something like 9 to the x or 4.2 to the x, something like that. And here's the exponential function defined. Again, so we're going to do some algebra first, and then we'll get into our derivatives and antiderivatives. So a has to be positive for that to make sense, a real number, and it can't be 1. Those are the conditions. Then the exponential function with base a is a to the x, and it is defined as a to the x equals e to the natural log of a x. This is one of those, like, this is the definition, this is where it comes from. We don't really do much with it. We can come back to this definition to talk about where did the derivative come from in terms of chain rules and so forth. So that's kind of helpful. But we're not going to actively participate with this properties definition the way we have it on some of the other ones. Okay. And then the logarithmic function of the same variety talks again about the fact that a is greater than 0, it's a real number, and it's not 1. Then the logarithmic function with base a is log base a of x, and it is defined as log base a of x equals the natural log of x divided by the natural log of a. And usually when you encounter these for the first time in maybe an Algebra 2 course or a trig course or something like that, college algebra perhaps, you see this log base a of x is ln of x over ln of a when they talk about change of base formula. That's where they usually introduce this idea instead of introducing it sort of in the way that we have. It's valuable to notice that the reason that these can be rewritten in terms of natural logs, whether it's here or whether it's here, is because you have a natural log in your calculator. Over here, there is no log in your calculator. The log in your calculator is log base 10, so it's what's called the common log, but there is no way in most of your calculators to force that subscript to be something besides 10 or e. So the manipulation for that in most cases is done like this with most scientific calculators, okay? So we have the natural log, log base a of x is the natural log of x over the natural log of a. So logarithmic properties actually match the same as the other log properties that we've had. So, logs, whatever the base is of things that are multiplied can be separated with addition and addition. Logs that are subtracted can be separated with, logs that are divided can be separated with subtraction and so forth. There are some inverse properties, though, that you should sort of be aware of. And again, they look a lot like what we did with base e. They don't look any different. They just have an a where the e's were. So if y is equal to a to the x, this is true if and only if x is equal to the log base a of y. And you remember we drew scorpion tails to kind of show how we could think about this. And you could rewrite a to the power of y. Sorry, I drew it the wrong direction because I've got it written the other way. It needs to land right beside itself. That's what I should have drawn. I apologize. A to the power of x, which is what's on this side, is equal to where it lands next to it equals y. The second property is a to the log base a of x is equal to x. So these are inverses. They cancel. We're left with the exponent only. And log base a of a to the x, you can think about this x coming to the front. But again, these things cancel, and we're left with the x only as the exponent. So we saw that happen with base e. That is not new. It's just doing it or showing it can be done with any base a. This satisfies the requirements, right? Positive, real number, not equal to 1. So the first thing we're going to do is we're just going to do some manipulation and solving equations using that manipulation. So here's our first one. It says log base b of 27 is equal to 3. There's going to be more than one way to do most of these. I tend to do things in a visual way. So when I look at this, I see, okay, that b is sort of stuck, and I don't want it to be stuck in a base. And if I don't want it to be stuck in a base, I have to have a way to manipulate it to get it out. And I can do that with this property number 1. It allows it to come out. So do you see how this a right here is in the subscript? And this a is the base, but it's no longer a subscript, right? So I can manipulate this as well. I start with the b and I draw my scorpion tail around. I always land right next to the value that's beside the log. So this b is raised to the power 3, turns into an exponential, and it lands, or it ends, at the 27. You might be able to just look at this and see it. In fact, you probably can. So my college algebra students or trig students probably can't. And so we would work a little bit harder to develop why this is happening. But one thing you could do if you didn't see it is you could take the cube root here. Your calculator will tolerate that just fine because this is a very beautiful cube root. What is the cube root of 27? It's 3. Now, you don't have to draw on the cube root. If you just can see that and you say, oh, well, this is 3 cubed. That's what 27 is. You just write 3 down. That's fine. Okay, so I don't need to see the cube root of 27. But there's going to be ones that maybe are going to be a little bit more complicated or harder to see, and you might want to draw a little bit more out to remind yourself what your step you're doing. Okay, any questions on that one? All right, so back in section 1, we talked about log properties, and we're going to actually use the log properties in this section a fair bit, at least in this example, and there's going to be some in your homework like this. So when we see 2 separated logs like this, right, this log over here and this log over here, we don't want to deal with 2 or 3 or however many logs in a problem. We want 1 log in a problem. So we're going to consolidate, if we can, or condense the logs. So since these logs are added, what can we do to the insides or the interiors of the logs? We can't add them, but you're thinking along the right idea. We can multiply them. Okay, so because the logs are added, we can multiply the insides of the logs. So this property looked like this. I'll write it in terms of natural log because that's how I think we had written it before. So the natural log of A plus the natural log of B is equal to the natural log of AB. That's the property we're using. So I can rewrite this as log base 3 of the x, and the x is multiplied by the x minus 2, and it's going to equal 1.
Can I presume that property only counts if they have the same base?
Yes, you're correct. The same base is required for that to work. Good observation. I can't think of any case where they try to do something different than that. I could be wrong, but I don't know that you're going to see anything like that. But that's a good observation, yes. Okay, so now the x, right, the variable is sort of trapped inside. It's not trapped in the base like it was a minute ago in the last problem, but it's trapped inside of a log. I mean, it started out trapped inside of a log anyway, but it's also still trapped inside of a log. So I need to get it out, and the way I can get it out is by changing this into an exponential with that scorpion tail. So that 3 is now the base. The opposite side is the power 1, and then it lands back onto the inside of the log, which is x times x minus 2. Okay, is everybody good? Rewriting steps okay. Now, don't be tempted to go doing something that's not okay algebraically. 3 to the 1 is 3, that's fine. But I can't just separate each of these and set them equal to 3, right? That's a property that only works if it's equal to 0. 3 is not 0. So I have to actually get everything on the same side because I'm going to have x squared when I distribute and multiply this out. This is x squared minus 2x. And in order to solve a quadratic, right, anything bigger than linear, to be honest, we need everything on the same side and then factoring. Okay, so we're going to subtract the 3 to the right. So I have 0 equals x squared minus 2x minus 3. You're not going to see a whole lot of factoring in Calc 2, but it'll come up from time to time, and we're going to assume that you remember how to do that. If you're struggling with that or just the details are kind of a little fuzzy, that's a good thing to start. Ask somebody, remind me how I do that factoring bit again for this, and we can do that. So how does x squared minus 2x minus 3 factor? Well, the x's are there. Okay. The negative at the end with the 3 tells us that we need one sign that's negative and one that's positive. Otherwise, we won't multiply the ends together to get negative 3. And then I need 2 numbers that give me 3. Well, 3 and 1's it, right? I just need to make sure I put them in the right place. For example, if I put a 1 here and a 3 here, it doesn't work. Can you see why?
It doesn't add a negative 2.
Yeah, it doesn't add a negative 2. What's it add to? Positive 2. So if that's the case, it means my 3 and my 1 are in the wrong places, or you can say my signs are in the wrong places and you can switch those. So I'll switch my signs, but you could switch the numbers just as easily. Now does it work? Yeah, it does. And I set each of these equal to 0, right? So this gives me x is equal to -1, and the other one gives me x is equal to 3. Problem is, one of those answers actually doesn't work.
Because it has to be a positive number.
Okay, why do I need a positive number here? So you're exactly right. This is not going to work. I marked out the wrong one. I'm sorry.
Because
Wrong. This is not going to work. Yes, go ahead.
dropping it from the base step is step two. The first step we did only works if we only count positive numbers.
Okay, so the very first part where I was actually given my problem, I need to have values inside of logs that are positive. The domain for logs are all positive numbers, right? I can't have negatives inside of a log. So if I try to put the number -1 in, I would have a log of -1 on one piece, and I'd have a log of -3 on the other one. I can't have logs of negatives. So while that sort of came about as possibly an answer, it's got a name. It's called an extraneous solution. Extraneous means that my algebra made it work in the end because I've manipulated some things that don't actually work in the original problem. So I only end up with one answer. My answer on this one ends up being x is equal to 3. You could end up with two answers that are both fine. You could end up like we did here with one that's fine and one that's not, and you could end up with nothing that works. So no solution is a viable option here. This one ends up giving me one value, x is 3. And you should be able to check to make sure that it actually works as well, not just that the 3 is a valid value to put in, but that it really works. If I had log base 3 of 3, and if I had plus log base 3 of 3 minus 2, log base 3 of 3, that's actually got the value of 1 because the 3 and the 3 are counteracting each other, right? They're inverse operations. And then over here, I've got the log. This is the number 1. The log of the number 1 is 0. So I have a 1 plus a 0, and it's going to equal to 1. So we should be able to check it as well like that if you want to confirm that the value really worked, not just that it didn't error out. Okay, ready to look at another variety? Okay, this variety does not start out with any logs in it, correct? In fact, you might recognize this formula. This actually comes from compound interest. So A equals P times 1 plus R over N to the NT. Okay, so if you're looking at that and you're like, I think I've seen that before, you probably have. So this comes from compound interest. Setting this equal to 2 actually comes from looking for something called doubling time. So this is a direct result of some kind of an application involving interest and doubling time. We're asked, however, simply to solve for t. And t, again, is sort of stuck. Right? It's stuck in a location that's not easy to be solved for. It's stuck in an exponent. I don't want it in an exponent. I want that exponent to be down in front. Well, how do I get exponents to move down in front? Well, I need a log that allows that to happen. So we're going to put, there's more than one way to do this, by the way, again, but I'm going to put, we'll just use natural log. It works as well as anything else. Put natural log on both sides. So that allows me to take this exponent and to pull it down in front. So now my exponent 365t, natural log of 1 plus 0.1 over 365 is equal to the natural log of 2. Now you are welcome to figure out what 1 plus 0.1 over 365 is and put that decimal in, but if you decide to do that, and it's okay, you need to put in lots of the decimals because it is a very long decimal expansion. It's really ugly, and you don't want to round too quickly. If you round too quickly, oftentimes that will affect your answer in the long run, and it'll be off. So if you decide to go ahead and figure out what that value is equal to, plan to write down a bunch of decimals. And what I mean by a bunch, at least 6, if not more. Okay, so a bunch. And so I actually do have a bunch of the decimals written down. I think I'll go ahead and do that since I mentioned it. So this is 365t, and the expansion inside is 1.00027. I've got more than 6. 39726. That's what I have. Equals the natural log of 2. Your calculator can tolerate that. It can find the natural log of that value. It can find the natural log of the value without you doing a decimal approximation and stopping it as well. So if you want to type in natural log of and put in parentheses 1 plus 0.1 over 365 and do all of this at the same time, right here, you can do all of that at the same time. So that's what I'm going to do next. I'm going to type in the natural log, and I'm going to type in the exact value, which was the 1 point plus 0.1 over 365. And it's so small, my calculator turns it into scientific notation. Okay, my calculator says 2.739350791, and it says capital E -4. It's scientific notation. But that expression, whatever it is supposed to be multiplied by 365, right? It's also supposed to be multiplied by t, but I can multiply numbers. The variable is what I'm looking for. So in my calculator, I'm going to hit times 365. And when I do that, my calculator spits back out an actual decimal approximation instead of the scientific notation version of it. And let me just write down for you what it tells me. It tells me 0.0999863.039. Okay, and I'm just going to keep it in my calculator in that form. I don't need to stop it. I don't need to type it in again. What am I going to do then to solve for t? We're just going to divide, right? We're going to divide by that very long expression. So it's going to look like that. Okay, so that leaves me with t on the left. And in your calculator, I'm going to try and show you calculator tips along the way. We're not focused on the calculator, but using it effectively is a good tool. So again, I've got that expansion of the 0.09s in my calculator. If I type in natural log 2, my calculator forces a parenthesis to open before the 2, and I'll push after the 2. And I'm just going to hit divided by. And I don't want to type in all that expression. If you want to, that's fine. It's not going to hurt anything. But if you want to avoid it, you can hit second, and then the little negative button at the bottom is the A and S key. And that'll take the previous answer and make it the divisor in its entire beautiful form, or not so beautiful. And if we press enter, it's actually going to give us the value that we're looking for. And we'll round to 2 decimal places just because it doesn't tell us any differently. Usually it will tell us. Mine, if I round to 2 decimal places, is 6.93. Yes. Oh, it does at the top. I am so sorry. I do not have it on my screen. Oh, it's because it's the directions on the previous page. Thank you. So 3.2. Good catch. Okay, so 6.932 is the decimals. And what this is in the context of the problem is it's actually telling you that it takes almost 7 years for that money to double. With the conditions that are showing up inside of that problem, by the way. Okay, so this is all algebra. This is all stuff that we teach in college algebra at this school, actually. It's part of our college algebra curriculum. But we, as we've been doing on all of these, are starting out with a little bit of the college algebra and then moving into the calculus that comes from this. So the next component then is to talk about derivatives, and we will end with antiderivatives. So derivatives. If we have the derivative, or if we have f of x is equal to a to the x, okay, it's kind of like with e to the x, right? The a to the x is part of its own derivative, a to the x. But we get an additional component that's natural log of a. Okay, so we get a coefficient multiplier, a constant multiplier in front, ln a. And if we do the log base a's derivative, we get 1 over x, right? Just so ln of x would have been 1 over x. That's the piece showing up again. But we get an additional coefficient multiplier or constant multiplier in the denominator of the natural log of a. And I would like to show you where this comes from, because it's not coming from nowhere. It's coming from the way that we defined these guys to begin with. So once you get it jotted down, we're going to flip back to the very beginning of this lesson so you can see where those pieces come from. Okay, I think we're good. Yeah? Okay, so come back over here to the very first slide after, the title slide. Do you see when we defined a to the x as e to the natural log of a to the x? There's a property of logs that would allow us to, well, actually, let's just do the derivative as it is. If we do the derivative of e to a power, it's e to that same power, right? And then I need the derivative of the power, and the derivative of the power, when it's natural log of a times x, would be, I'll write it in front since I'm out of space at the end, the natural log of a, because that's the constant in front of the value x. Well, this e to the natural log of a business was a to the x, and there we have natural log of a times a to the x as our derivative. Okay, so this is our derivative. If this is our function, then this is our derivative. And the same thing happens with our logarithms. Right? If we wanted to take the derivative of the log base a of x, and it's thought of this way at the end, well, the derivative of the ln of x is 1 over x. And ln of a is just a constant multiplier. It just comes along for the ride. So there's ln of a still right there. But when we have denominators embedded like this, or denominator divided by denominator, it's the same thing as having those two denominators multiplied. And we see that it shows up exactly like we were expecting, again, from the derivative formula on the other slide. Okay, so that's where they're coming from. They're coming from the very definitions of what these guys are. Okay, so now we're going to take some derivatives. Okay, so we see 2 to the t. That's obviously going to be an exponential rule. That's our new one. But what else do we see happening here? What's the overall rule that we're going to have to deal with for derivatives? Not chain, product. Yeah, it's a product. So the two pieces that are being multiplied, I'll kind of separate them out like that. I've got 2 to t squared in front, and I've got 2 to the t at the end. Okay, these two pieces are multiplied. So to find my derivative means that I'm going to rewrite the first piece, t squared, and then I'm going to take the derivative of 2 to the t. Well, the new rule that we just learned is that the derivative of 2 to the t is 2 to the t ln 2. 2 to the t ln 2. And then I'm going to reverse. The derivative of t squared is 2t, and then I rewrite the second piece as 2 to the t. Okay, so a couple things about this. Careful on your t's. Derivatives and antiderivative, the gateways are all in x's, so that's not going to be a problem. But can you see how if you're sloppy that this could end up looking funny at the end? 2t and 2 to the t? You're going to have to be careful in how you're writing so that we can distinguish which one is a base and an exponent versus which ones are being multiplied. For the purposes of the gateway, you would do nothing else. For the purposes of what we've been doing in class, you at the very minimum would want to move the coefficient to the front. This natural log of 2 would move to the front. Putting it in parentheses is often helpful just to distinguish it from the things that are happening next. Not necessarily that it has to be done, but you'll usually see it done. And this is t squared 2 to the t, plus now we have a 2t 2 to the t here at the end. Aside from that, you don't have to do anything else. You're just shifting the coefficient to the beginning. The only other thing that you might see is if you were asked to continue on the process of this, you might see something factored out to maybe make it easier if you wanted to do a second derivative or something like that. But it doesn't simplify anything. It just changes its form. So this right here would be where we would leave it for the purposes of what we're doing as a general statement. Okay? Okay, let's try another one. All right, so this does not have a subscript. It just says log. So what's the subscript? It's 10. If you see a log with nothing written as a subscript next to it, not ln, but log, it means log base 10. Now, we're going to need to know that because we're taking a derivative of this guy. So I'm going to write it in as a reminder. This is log base 10 of x squared minus 1 over x. Now, this is just like what happened in section 1. Okay, when we did 5.1, we talked about the fact that you could take the derivative here if you wanted to. But if you did, you've got a quotient rule, correct? And we'd like to not have a quotient rule if we don't have to. It's kind of messy, right? It makes things a little complicated. The messier things are, usually the easier the mistakes are to make. So if we could do something to separate this out, we'd like to do that. And that's what we're going to do. So what property, How can we use the properties of logs to separate this out? Subtraction, you got it. So we're going to do log base 10 of x squared minus 1 minus the log base 10 of x. Now we do still have a chain rule in that first piece, correct? Yeah? It's even in parentheses. You can see the parentheses there, right? The inside function. And you can't separate what's in that parentheses out because we can only separate out multiplication and division. And that's neither. It's subtraction. So we can't do any other separating. We've done all the simplification with logs that we can do. Now we have to actually take the derivative. So what is our derivative of log base 10 of x squared minus 1? Well, we're going to have a 1 over natural log of 10 because that's part of the derivative formula. And then we're going to have a 1 over x squared minus 1 because that's the derivative of logs as a general statement. And then we're going to have the derivative of the inside of x squared minus 1, right, that piece, which is 2x. Feel free to put some parentheses in there. I've just put some dots in there, whatever it is that makes it feel more comfortable to rewritten that way for you. Now, log base 10 of x, that's the easier one to do because there's no chain rule. I'm going to have 1 over the natural log of 10. And then I've got just 1 over x. There's no chain inside to take the derivative. Or if you thought that there were, it would just give you a 1 at the end. So feel free to write times 1 if you'd like, but it's not necessary. Okay, gateway, you stop there. It's messy, it's ugly, we don't do anything else. The only things that we can really do in terms of cleaning it up, we could move this 2x up on top if we would like. That would be a good thing to do, right? It'd be consolidating it a little bit. The natural log of 10 and the x squared minus 1 can go beside each other in the denominator. You do need some parentheses for that to make sense. Otherwise, it will look like the 10 is multiplied by the x squared, but it's not, right? It's the natural log of 10 that's multiplied by everything. And we can do the same thing over here. This is 1 over the natural log of 10. Again, either the parentheses here and then put an x, or if you wish, the parentheses around the x. It is more typical to see the parentheses around the natural log of 10 in that case, but either would be acceptable. If you want to say, oh, what about parentheses over here? Go for it. Put some parentheses in. They're not going to hurt anything, right? Now, could we consolidate these back together? I mean, we could, right? They're fractions. We could get a common denominator. We can get the numerator. We can do all of that, but it doesn't simplify anything. So it's not necessary. Okay? Yeah? You guys look like you really want to simplify. No? No, okay, just checking. All right. Do you remember something called logarithmic differentiation? Yeah. Okay, so logarithmic differentiation was done back again in section, I think it was section 1. And we did it for the purposes of not being able to take the derivatives the way they were written, or it was simply really awful and ugly to do so. And log properties allowed us to simplify something. That's why we did it. Now, this is the first case. I cannot take the derivative here. And the reason I can't is because I have x acting in two completely different ways. In one place, the x is acting as the base, right? And it's also part of its own exponent. I can't take the derivative directly here. It's not possible. Okay? So what do? Well, logarithmic differentiation had us taking a log on both sides. And you can use whatever log you want. I kind of, if I'm given the choice, I'm just going to use natural log because it's shorter to write. It looks a little cleaner. And so I'm going to default to that one, and I'll do the natural log on both sides. Okay. What property of logs am I allowed to use then, or am I able to use?
Take out the exponent.
Yeah. The exponent can come down to the front. That is a log property. We're not doing derivatives yet. This is just manipulating with logs at the moment. So I've got the natural log of y equals 2 over x times the natural log of x. Okay, everybody good so far? Okay, there's no more power to a power with variables in the base and the power anymore, right? We don't have that anymore. Yeah? In fact, we have an x that's sort of embedded inside of a log, and we have an x that's a multiplication factor out in front. That's how they're written right now, and I can deal with those. I do have a product there, right? These two things are being multiplied, so I'm going to have to deal with that part of it. But I can do that. It's not too ugly. It's product rule. All right, so we're going to work through. We've got the natural log of y. Okay, so starting on the left, we can't just write y prime, right? Because we've got the natural log of y over there, not just y. So what is the derivative of the natural log of y? 1 over y, that's part of it. And then we need dy dx, because it is implicit differentiation at that point. Your favorite section from Calc 1, I know, right? Dy dx is showing up. Okay, on the right-hand side, there's no y's, so over on the right-hand side, it's just going to look like our product rules that we've been working with since, the middle of Calc 1 anyway. So we're going to take the first piece, and I choose to rewrite my first piece. And then I want the derivative of the second. So what's the derivative of natural log of x? 1 over x, very good. And then we have addition with products. Now I need the derivative of 2 over x. Now, that's fine, but it might be more helpful to remember that it's written like this, 2x to the negative 1. So that's how I'm going to think of it. What is the derivative of 2x to the negative 1? Yep, negative 2x to the negative 2, which we'll rewrite and clean up in a little bit. Yep. And then we need the other piece, which some of you are already telling me was the natural log of x at the end, right? Okay, are we good? Now, it's really ugly looking, admittedly. So we're going to clean things up a little bit. I have 1 over y times dy dx. There's no implicit differentiation on your quiz on Friday or Thursday. None of that happens on Gateways, okay? So this is an outside of the quiz kind of situation. This one is actually 2 over x squared, right? 2 over x times 1 over x is 2 over x squared. And then I have minus, and I actually end up with another 2 over x squared, don't I? And then the natural log of x. Okay, so we're not done with these until we have dy dx on its side by itself. And right now, I've got more than dy dx on the left. So what am I going to do with the 1 over y? I'm going to multiply it. So we're going to multiply by y on both sides. Okay, nope, no more space over here. So let me make this cell smaller. All right, but y'all know what y is. What is y? Yeah, it was given to us at the beginning, right? Y is x to the 2 over x. Okay, so that looks awful. There's really not a lot we can do to simplify or to clean it up. It's probably worth noting that we can do one thing that actually is quite reasonable. We saw that it have one piece in common. These pieces are the same, right? We could factor that out to clean it up a little bit. Again, is it absolutely necessary? It's not absolutely necessary, but it is going to look a lot cleaner if we do. So I'm going to do it on the screen here for this one. If you don't happen to notice that on a test or a question or something like that, don't worry about it. But it wouldn't be taking off any points. But it does look nicer. If I take that out of the 2 over x squared, the first one I get a 1, and the second one I get a natural log of x. And then I still have x to the 2 over x at the end. So it does look a little bit friendlier in that form, but the previous form would have been okay too. Okay, any questions on that? Yes?
We left it as y, we did 1/6.
Yes. If you leave it as y, that's not going to work. Good question, Andrew. Yeah, the y, because we know what it is, right? It's not a function that we're given. Like when we did implicit differentiation back in Calc 1 and whatever Calc 1 class you took, undoubtedly you encountered some things where you could not have cleanly solved it for y. It was not given to you at the beginning as y equals. That's not what we're going to be encountering here. We're going to be encountering something where we know what y is. So we will at the very end put the y back in on ours. Yeah. Okay, you ready to look at antiderivatives? Okay, so we've done this before. Slight variation because we're actually looking at the antiderivative now of a over x. So the derivative, let me remind you, if I were taking the derivative here, it would have looked like this. It's a over x, and then it's times the natural log of a, right? That's what we just learned the derivative was. If we're doing the antiderivative of a over x, a to the x, excuse me, we see that the a to the x is still part of the antiderivative, just like it's part of the derivative. But instead of multiplying by the natural log of a, we end up dividing by the natural log of a. So probably, and if you were in my class, I know this to be true, when you learned about antiderivatives, your teacher probably talked a lot about the fact that it's just the inverse, right? It's the opposite. If you multiplied something in the case with derivatives, you're going to divide it in the case with the antiderivatives. That's what we see happening here. We multiplied by ln of a when we took the derivative. We're going to divide by ln of a, or write it as 1 over ln of a when we take the antiderivative. Okay? Notice what we don't have. We don't have two antiderivatives here that we've added. We just have the antiderivative of a to the x. We don't have the antiderivative of log base a to the x. But if you'll remember, we didn't have the antiderivative of the natural log of x either. We will encounter those guys, but we won't encounter them until chapter 8. They're not clean, they're not simple, they're not easy to do. Okay, so there's not a closed form that we learn in this chapter about it. Okay, so let's do some examples. We're going to find the indefinite integral, and you're going to see values that look similar, right? X and 3, but they're operating in different ways. This is x to the third, and it's 3 to the negative x. You know how to take the antiderivative of x to the third. We've been doing that now for a little while. So what is the antiderivative of x to the third? Not the derivative, the antiderivative. X to the fourth over 4. Very good. That's the antiderivative. Everybody remember? Okay, good. The other piece, though, 3 to the negative x, that's our new property. We have a variable exponent and we have a constant base. The base is a number, the exponent's the variable. That's this new property. And it's going to take a minute because we're not used to seeing them written that way. We're used to seeing the reverse of that. So if the base is the number, then we have this antiderivative form. This says the piece that's raised to the power is going to stay the piece to the power. So we're going to have 3 to the negative x. That's going to be part of it. But we also need to divide now by the natural log of the base. And what's the base? 3. Now there's one more thing here that's going on. What is it? What is it? Okay, we need a plus c. Something else. That's true. I wasn't there yet, but you're right. We need that. There's a negative x up there, right? It's not just x. Correct? If it were x, we didn't have the negative, we would be done and the problem would be over. But it is a negative x. So this is one of those very unexciting U substitution things going on. So I'm going to show you what it is right here, and then we're going to cut to the chase at the end and see what we can really do on a statement on like this, so we don't have to see the U substitution because it's not very exciting. The U substitution happening is just with this piece. U is equal to the negative x exponent. Du would equal to negative 1 dx. And we would need a negative du to be replacing the dx on the other side. So what it does when I divide by, or when I have that negative x exponent, is it introduces a coefficient of a negative 1. You can put it at the end, you can put it at the beginning, but I introduce another negative 1 because because there's a chain rule there. It's just not a very exciting chain rule, which is why we can handle it. I've got a negative 1 that's going on there. Okay, so do you need to show the U substitution? Well, heavens no, especially not with just negative. When we have a negative exponent, it's just going to introduce another negative into the equation, or into the problem, that part of it. This works just fine. You can write it like this. If you want to, and for sure on the antiderivative, when we do get to the antiderivative quiz on Tuesday next week, you got to have the plus c's, just like Joshua was saying, got to have the plus c's. The only other way to clean this up at all in terms of homework and so forth is that it's kind of ugly to have it written with that negative 1 where it is. I don't know what I meant to, sorry, it's just be a 4 down there. It would kind of just be nice to put the negative out here. And then 3 to the negative x over natural log of 3. Right, so just moving this negative to being in the front with the positive, and it becomes a subtraction sign. So that's a little cleaner, makes it look a little bit nicer. Okay. Yeah.
Would I not take the negative exponent down since it's like, I don't know. I've always
Oh,
thought it's
okay.
like that.
So that's a very good question. So Isaac's question has to do with the fact that we have 3 to the x as a negative x exponent. And are we okay to leave the answer that way? So this is kind of along the lines of radicals with variables. When the exponent's negative, but it's a negative variable, you can leave it there because it depends on what the variable is. If the variable itself were negative, the exponent wouldn't really be negative. If you changed it like this, you could do that too. It wouldn't be wrong. And in fact, you might see it written that way in terms of like a solution to something, or if WebAssign spits you out something and doesn't match what you thought it was going to be or whatever. That's perfectly fine as well. But either of those options are okay because we don't know the value of x. Yep, great question. Okay, let's try another one. This one looks more complicated because it looks like there's an inside function, there's some product, something going on. It looks really ugly. We don't have a lot of tools in our tool belt to deal with this. We have things like algebra and trig simplification, which don't look like, well, trig doesn't look all helpful here because there's no trig involved, but algebra simplification is not going to be helpful here either. And the only other tool in our tool belt, which is the one we keep sort of hammering into the ground, is u substitution, right? Keep going back to the u substitution. Well, if we're going to, and we are going to do u substitution here, what would u be? The exponent, right? The part that's in the exponent is going to have my u substitution. And the reason is because it's got a power of 2. Do you see that power? That power of 2 is the red flag for it. There's also parentheses there that sort of lead us to it, but there's parentheses at the beginning too. So there's parentheses in 2 places, so that doesn't necessarily help in this particular one. But that exponent with the square is in fact going to be helpful. So what is the derivative then of 3 minus x quantity squared? And I don't want to distribute that out. Like I don't want to multiply 3 minus x times 3 minus x and then go from that direction. That's not going to be real helpful.
2 parentheses 3 minus x and times that by -1.
Yes, sorry, missed that first. And then the dx on the end. Yes, you got it. And the reason that that's nice is because we exactly have that 3 minus x in the beginning of our problem. This piece is here. That's why we don't want to multiply it out. So in other circumstances, we might want to multiply it out before we take the derivative or something like that. But in here, it doesn't end up being very helpful to do so. The pieces that I am still including over here can get divided to the other side. So we're going to divide those to the other side. So this is divided by -1/2. Multiplied by -1/2, divided by -2. That leaves me with the 3 minus x and the dx. So we end up being able to take the 3 minus x and the dx out. They get replaced by the -1/2 at the beginning and the du at the end. And the 7 is still here. Don't lose the 7. And it's 7 to the u. So we still have our -1/2. What is the antiderivative of 7 to the u? Okay, it's going to have a 7 to the u, and it's going to have an L and a 7. Where the L and a 7 going to be? It's going to be on bottom. Since we're taking an antiderivative, it's going to be on bottom, natural log 7. Okay, I need a plus c. I need to change my u. There's a couple things I still need to do. You can do them in whichever order you'd like. I'm going to rewrite this as negative out here in front. I'm going to put the 2 in the bottom. I don't even need the 1 up here, actually. This is 7 to the u. I'll replace it in a minute. And this is natural log of 7. And then we will replace the u with what u is equal to, which was 3 minus x squared. We're dividing all that by 2 natural log of 7. And we do need the plus c somewhere along the way. Here's as good a place as I need to put it back in. There's one other thing that denominator could be written as. Again, I'm not suggesting you need to at all, but do you know what else you could write instead of the 2 natural log 7? Yeah, say it louder. Yeah, Elijah has a 7 squared, right? That 2 in the front could make it 7 squared, and 7 squared is 49. So you could have natural log 49 in the denominator. as another version of this. It's not any better. It's not any more simplified. It's just another option. Okay? Yes?
On a test, if we're like working this out,
Yep.
we're doing the U substitution, like have an M plus C like that. would
Yep.
take off?
It doesn't matter where you put the plus C in. So if you want to write it along the way, that's fine. As long as it's in your final answer, I'm good with it. And the reason is because when you're substituting, to be perfectly honest, the C here and the C here are not the same C. Because one is in terms of U and one is in terms of X. So it could be argued that you shouldn't put it on until the end. And it could be argued that you should be putting it on along the way. It could also be argued that you could call one of them C1 and the other one C. None of this is that important to me. As long as you've got it on at the end, we're going to call it good. Is that all right? All right. Now I mentioned compound interest, so I want to bring this up again because this is an application of what we're doing. Compound interest, if you'll remember, is A equals P times 1 plus R over N to the NT. I said that one out loud earlier. P is the principal. Principal means how much you borrowed or you put into the bank, like you invested. R is your interest rate. Remember, it has to be done as a decimal. So if it's 5%, it's 0.05. T is time. Time is always in years. So if somebody talks about 18 months, we need to turn it into the 1.5 years that it corresponds to. And then A is the amount that you would have or owe after that amount of time. And then continuously compounded interest, down here at the bottom, is A equal P E to the RT. Now, continuously compounded interest is not used for actually compounding interest, but it does give us information about inflation rates, which is definitely a thing in our society right now, right? Got a lot of inflation going on. So there is application for it, but not in terms of investments. And then, so these you've seen before. This shows up in college algebra, okay? You may not have done anything with it for a while, but we saw an application where we were solving doubling time something a minute ago. There's one other kind of application problem that's going to show up that you may or may not have seen before. It's called a logistic function. A logistic function has the formula f of x equals capital L over 1 plus a e to the negative bx. L is called the limiting value, or it's sometimes called the carrying capacity. If the b value is positive, which means the exponent is negative. I'm going to say that again. I want to make sure you look at what I'm saying. If the b value is positive, can you see that the exponent will be negative? See, there's a negative in that formula. B value is positive means I actually have a negative exponent. If that happens, I have an increasing graph, and the graph looks something like this. And it is limited. There is a limiting feature to this. It's balanced right up here, or bounded, right up here at L. And if the b value is negative, so if you put a negative number in for b, there's already a negative in the exponent. I actually end up with an exponent that's positive, if that's the case. I end up with a graph that looks something like this. Okay, it flips it around. It still has a carrying capacity or a limiting value of L. It's just happening on the left. So there's an application problem that's going to ask you in your homework. I think it's in the homework. And I want you to know what this actually does, or where this is actually showing up, because this is like biology. This is showing up as a biological application. So in Oklahoma, we have lots of deer. Did you know that? Have you hit one before? We have. We totaled our car 2 years ago on Labor Day weekend coming back from the lake. And deer was out in the middle of the day. They're not actually out in the middle of the day all that often, but yeah, we totaled the car. Okay, so we have lots of deer. So if you have deer, and this is just an example of one inside of a population, there is a limiting value that the environment can support. Okay? It can only support so many deer. Now, I don't know what that number of deer is. Biologists could probably tell you in a specific given environment, but there's a carrying capacity. They have to have so much space. They have to have so much food and water. There are limits upon what the environment can support. That's a limiting capacity. That's this first graph, right? That's what happens with these kinds of graphs. And in fact, this is the kind of graph a lot of people were looking for when COVID happened. Eventually, enough people have to have this that you're tapering off the deaths or the new cases or whatever you were looking at. Eventually, it's got to taper off. The question was simply, when will that happen? I only made a no, but people kept waiting and looking for it, right? Okay, the other one is actually the opposite, right? Something's dwindling, but it dwindles down, but it doesn't ever dwindle down to absolutely ground zero, nothing, right? So if you think about different kinds of, environmental things where extinction happens, this takes a long time before we actually end up with things extinct. They level off before we get to zero usually, and they end up with a really small leveled number at the bottom, okay? So these are our two logistic graphs that I want you to be aware of in the application when you see them.